Can we simply create super intelligent AI large language models by letting them talk to one another? This video will give you the answer based on the original lecture Multi-Agent AI presented by Norm Brown, who is an expert at OpenAI right now. Hello everyone, my name is Pisek or Benz, and this is 𝐀𝐥𝐸.
Hello from 𝐀𝐥𝐸. This is a summary of a lecture titled Multi-Agent AI. So today, we're diving deep into the world of AI agents, and we're going to tackle a question that, it seems pretty simple on the surface, but once you start digging, it reveals this absolutely huge challenge for the future of AI.
Okay, so you probably remember the story of AlphaGo, right? The AI from DeepMind that taught itself to become the world's best Go player. Just by playing against itself, it was this monumental, mind-blowing achievement. And that gets you thinking, why can't we just do the same thing with large language models? LLMs. Why not just pit two of them against each other in a debate until one of them or both becomes super intelligent? Well, as we're about to find out, the answer is the real world is a lot more complicated than a Go board.
So let's look at this comparison. Because on the surface, the path AlphaGo took looks like a perfect blueprint for what we're doing with LLMs today. And that's exactly what makes this analogy so powerful, so tempting. It really feels like we're just one tiny step away from the next giant leap.
And here's that blueprint laid out. Step 1 is pre-training. AlphaGo, it learned from a ton of human Go games. LLMs, they learn from, well, the entire internet. Okay, check. Step 2, scale up the thinking power. AlphaGo used something called Monte Carlo tree search to look ahead. LLMs use chain of thought to reason through problems. Again, pretty similar, right? But then we hit step 3, self-improvement. This is where it all gets tricky. For AlphaGo, the answer was simple, self-play. But for LLMs, that's the big question mark, the missing piece. And it's because real-life human interaction, it's just not a simple game with a clear winner and loser.
And this is the absolute core of why that whole analogy just falls apart. We're making a huge leap here, from a nice, clean game of pure skill to the messy, unpredictable, kind of chaotic game of dealing with people. The rules are they're fundamentally different, and that changes absolutely everything about how an AI needs to learn.
So to really get this, you have to understand there are two totally different ways to think about winning. Let's use poker as an example. Imagine two players. Player A has a strategy that guarantees they will never lose a one-on-one match against any other single strategy in the world. That's called a minimax equilibrium. It's defensive, it's theoretically perfect, and it's what AI researchers have been chasing for years. Now, player B, their goal is different. They just want to make the most money possible playing against the real, flawed, sometimes irrational players you actually find at a poker table. That's a population best response. It's exploitative, it's practical, and honestly, it's probably what we want from a helpful AI. Now, here's the kicker. In a game like chess, those two players are the exact same person. In poker and in life, they are absolutely not.
And it all comes down to the type of game you're playing. You've got your perfect information games, like chess. Everything's out in the open. You see the whole board, your opponent sees the whole board, no secrets. But then you have imperfect information games, like poker. You have no idea what cards your opponent is holding, and let's be real, most of life, with all its hidden agendas and private thoughts, is one big imperfect information game. And here's a fact that might actually surprise you. Standard AI algorithms, the powerful ones, they fail to solve even a super simple game like rock, paper, scissors. You'd think that'd be a piece of cake, right? But no, they really struggle to find the best way to play. And why is that? Well, because there is no single best move. Playing rock is only a good idea if your opponent plays scissors. The actual best strategy isn't to pick one thing, it's to be unpredictable, to play each option about a third of the time. And it turns out typical learning algorithms are just not built to figure that out.
So all of this is building up to a pretty bold, pretty provocative claim. All those nice, neat, clean rules that work for a simple two-player zero-sum game, they just completely fall apart when you step into the real world, with multiple players and the need for cooperation. And this creates a fundamental, show-stopping problem for the idea of using self-play to teach an AI how to cooperate.
And here it is, the central claim from the lecture by Norm Brown at OpenAI. He says, learning to cooperate with humans without using human data is a dead end. And what he means is, you just can't learn how to interact with real people by only playing against a perfect, rational copy of yourself.
An AI that only does that is basically living in a theoretical bubble, completely unprepared for how messy, irrational, and just plain weird real humans can be.
To really see why, let's look at a classic experiment called the ultimatum game. It's a perfect example, and it's super simple. Imagine one person, Alice, gets $100. Her job is to offer a split of that money to another person, Bob. Now, Bob has two choices. He can accept the offer, and they both get their share, or he can reject it, and nobody gets a single cent.
Okay, so what would a purely rational AI, one trained on self-play, do here? Well, it finds the optimal solution. AI Alice offers human Bob just $1. A rational Bob should accept, right? Because hey, $1 is better than $0. The AI walks away with 99 bucks. Success. Except we all know that's not what happens. A real human Bob would see that $1 offer as a total insult, reject it just on principle, and boom, both players get nothing. The AI's perfectly optimal strategy is a complete disaster in a real human context.
Okay, so if pure self-play is a dead end when it comes to cooperation, then what's the answer? Where do we go from here? Well, it means we need a totally fundamental shift in how we think about this. We need a whole new paradigm for building AI that can actually, work with us. And the solution is this. We have to stop chasing that theoretically perfect optimal strategy. It's a wild goose chase. Instead, the real goal needs to be finding the population best response. In other words, finding the strategy that works best when you're actually interacting with real, messy, unpredictable human beings. And look, this isn't just some theory. It's already been proven to work with an AI called Cicero. Cicero managed to achieve human-level performance in diplomacy, which is this ridiculously complex 7-player negotiation game. And how did they do it? They followed this exact method. Step 1, collect a ton of human data and train a model to just imitate how real people play. Step 2, use that to build an even better, more sophisticated model of human behavior. And then, the crucial third step, run reinforcement learning, but train the AI against your human model, treating human behavior as just another part of the environment it has to navigate. Now, this is where things get really interesting, because all of this opens up the next great frontier. So far, we've been talking about AI cooperating with humans, but what about AI agents cooperating with each other? This is where the possibilities just explode. And there are two huge reasons why this is so exciting. The first one is all about speed, or latency. See, a single AI has to think one step at a time, and there's only so fast you can make that go. But if you have multiple agents, they can all work in parallel. I mean, just imagine 100 AIs tackling a problem at the same time. The second reason is diversity. Look, you don't expect one person to be a world-class expert in everything, right? We use tools like a calculator. It should be the same for AI. An LLM should be able to recognize a specific problem and just hand it off to a specialized agent that's the absolute best tool for that job. And what's really fascinating here is that one of the oldest, hardest problems in multi-agent AI, how do they talk to each other, has kind of been solved almost by accident. Because LLMs are built on natural language, well, they can just talk to each other, plain and simple. It's this massive built-in breakthrough that we almost got for free. So, the big takeaway here is pretty clear. Those clean, perfect, optimal solutions you find in games like chess, they're the exception, not the rule. If we want to build AI that can truly, genuinely cooperate with us, we have to stop running from the messy reality of human behavior and start embracing it. Now, a lot of the multi-agent systems we have today are still pretty brittle. They break easily if you throw something unexpected at them. But the fundamental pieces for something much more robust are starting to fall into place. And that leaves us with the final massive question. What's that one key insight, that missing link, that's going to transform today's fragile systems into the powerful collaborative AI of the future?
This video is a part of a series that will summarize the 2025 Agentic AI lecture series as offered by UC Berkeley RDI Center. For the full series of the summary lecture, see the description below. And don't forget to subscribe to our channel. We are on YouTube, LinkedIn, Facebook, X, and Substack. Subscribe so that you can get the AI insights that make your foundation or your organization solid. By the way, the lecture summary video is made with the help of AI, in particular Notebook LM, where I did my best to maintain its accuracy.